Hey everybody, I'm Jason Wang, and in this video I'll be showing you my attempt to implement QFT arithmetic. We'll get to what QFT is in a second. Woo, QFT. QFT is essentially, well, it stands for the Quantum Fourier Transform, and in essence, it is used to sort of convert from what you can see here as like a signal in the time domain. In this case, it would be a basic sine wave. And it converts from that into the frequency domain, where you can see the sine wave has a frequency of 1,000 hertz because it completes one full cycle in 1 millisecond. But it can the QFT essentially converts from the time domain to the frequency domain, and vice versa if you use the inverse QFT. And it's used a lot in signal processing and just sort of like you can break down a very complex signal into a number of frequency bins. Another useful way you can use the QFT is actually encoding like a number into a number of like a register of qubits. Essentially, well, qubits are the sort of quantum form of bits, but you can see they're obviously a little bit more than just that. In the computational basis, they can sort of be treated as bits. They go 0 and 1, 0 and 1. And you can see that like they essentially just count up like any normal classical bits. But when you use the QFT to convert it from the computational basis into the Fourier basis, you can see that it's actually based off of the rotation of these qubits, rather than just like up or down, on or off. And this turns out to be really useful for basically, well, first off, a number of algorithms, but also for just basic arithmetic, addition, multiplication, subtraction. Here's a circuit of the QFT. It applies a Hadamard gate and then a series of rotations, of controlled rotations, going down the line from the least significant bit to the most significant bit. You can see it does a controlled rotation, meaning that given that in this case, you can see x2 is a 1, then it will rotate x1 by some set amount, with R2 and R3, or as like Ri increases in value, it'll rotate more. You can actually see that in the next slide. The QFT adder has a very similar structure to the QFT in that there's a controlled rotation based off of another qubit. In this case, there's two input registers of the same length, but the second one is sort of affected by the binary value of the first input register. And so you get a sort of addition when you add like a rotation or add angle to the phase of the output register's qubits. And this can actually be sort of expanded further into the multiplication circuit, where the QFT multiplier actually uses like a weighted sum sort of thing, where it'll sum those two registers based off of another register. It gets complicated, but essentially you have your two input registers now with another one just sort of like set up as an output register. And you're just adding over and over and over again, much like normal multiplication works. But you do it via these controlled weighted sum blocks. And so if that bit of the first input register is true, then you can do, in this case, like one weighted sum, two weighted sums based off of which bit that is being rotated. Here we can see sort of the fruits of my labor. You can see that there's like an adder call and a QFT multiplication call. And you can see the results around here where we sort of go subtraction and then addition and then multiplication. The subtraction was just implemented by using the same sort of like 2's complement idea from like classical computing. But I use that in conjunction with my QFT adder to sort of replicate subtraction to a degree. This sort of comes with a surprisingly large cost, though. You can sort of see an estimate that I used. This looks like one of the more basic options available. It had a lower error rate, And I set my sort of bounds to be under the assumption that I wanted the function to run correctly 99.9% of the time. So these are pretty much accurate, like to the degree that I would really need, with relatively low run times. You can see well, this one ran in 18 seconds. That's pretty bad, but it's in the millisecond range, which is not horrible. But you can also see that they took quite a substantial amount of physical qubits, up to like 30K, I guess almost 40K total for this. And actually we can run it again and you can see sort of like more basic. This is sort of the basic, or I don't want to say basic, but the it takes the most qubits. Obviously, it's taking like 237,000, and it runs a bit slower. So it's probably the least ideal out of the options given for estimation, but you know. So why did I do all this? What's the point of all this? Why did I make an adder and a multiplier? Essentially, this QFT arithmetic is actually quite useful when building other quantum algorithms, and just like sort of in general, if you have like a superposition of qubits and you want to affect it to do arithmetic on it, without having to like collapse the superposition state with measurement, it's a lot more convenient to be able to run these sort of like adders and multipliers on that sort of like these qubit registers, rather than converting to classical and running them on a classical computer. You can see this is Shor's algorithm, and you can sort of, the period finding part includes a large amount of modular exponentiation, which, you know, is sort of like, well, it's essentially just multiplication many, many times. And so an efficient multiplication, given that multiplication is essentially the bottleneck of Shor's algorithm, is actually crucial to a more effective algorithm in this case. This sort of stretches out to other algorithms as well, other quantum algorithms that need some sort of arithmetic to be done, but don't want to collapse the superposition or just like switch context from like a quantum computer off to a classical computer, because there's always latency traveling between these two systems, obviously. And so having a sort of on-site quantum arithmetic engine is actually quite helpful. So from all of this, I had a few sort of like main takeaways out of everything. Mainly it was just experience coding in QSharp, implementing both the adder, the multiplier, coming up with how I would maybe affect these registers in QSharp or with 2's complement. I gained a lot of experience reading research papers and digesting sort of the content from these papers that are really geared towards people that already have a very dense sort of physics background, and being able to sort of understand what their intentions are, how their circuits are meant to sort of, what they're sort of meant to do. Even like some of their equations would like link back up to like an equation like 6 from like 3 pages ago. Getting into the hang of sort of digesting and reading these papers is really sort of like a large experience for me to be able to like use in the future. Another sort of fun sort of takeaway was the use of Microsoft Azure. I didn't actually get to use it to run my code on a real like quantum computer, but I did, like, if you saw the resource estimator earlier, that was a tool from Microsoft Azure that I could use when sort of developing and sort of optimizing how my code would run. In the end, it was sort of inevitably I had too much code, plenty to trim, but it was really a fun tool to sort of play around with and see just sort of like how these algorithms can sort of blow up into like huge sort of many qubit issues. Thank you.